We have designed and implemented the Google File Wise 10 GFS to meet the rapidly growing demands of Google's data processing needs. GFS shares many of the same goals as previous distributed file systems, such as performance, scalability, reliability, and availability. However, its design has been driven by key observations of our application work, loads, and technological environment, both current and anticipated, that reflect a marked departure from some earlier file system design assumptions. We have re-examined traditional choices and explored radically different points in the design space. First, component failures are the norm rather than the exception. The file system consists of hundreds or even thousands of storage machines built from inexpensive commodity parts and is accessed by a comparable number of client machines. The quantity and quality of the components virtually guarantee that some are not functional at any given time and some will not recover from their current failures. We have seen problems caused by application bugs, operating system bugs, human errors, and the failures of disks, memory, connectors, networking, and power supplies. Therefore, constant monitoring, error detection, fault tolerance, and automatic recovery must be integral to the system. Second, files are huge by traditional standards. Multi-GB files are common. Each file typically contains many applicable tie-in objects, such as web documents. When we are regularly working with fast-growing data sets of many TBS comprising billions of objects, it is unwieldy to manage billions of approximately KB-sized files, even when the file system could support it. As a result, design assumptions and parameters, such as I/O operation and block sizes, have to be revisited. Third, most files are mutated by appending new data rather than overwriting existing data. Random writes within a file are practically non-existent. Once written, the files are only read, and often only sequentially. A variety of data share these characteristics. Some may constitute large repositories that data analysis programs scan through. Some may be data streams continuously generated by running applications. Some may be archival data. Some may be intermediate results produced on one machine and processed on another, whether simultaneously or later in time. Given this access pattern on huge files, appending becomes the focus of performance optimization and atomicity. Guarantees, while caching data blocks in the client loses its appeal. Fourth, co-designing the applications and the file system API benefits the overall system by increasing our flexibility. For example, we have relaxed GFS's consistency model to vastly simplify the file system without imposing an onerous burden on the applications. We have also introduced an atomic append operation, so that multiple clients can append concurrently to a file without extra synchronization between them.